This is part 2 of the gas stoichiometry notes video. If you haven't yet watched part 1, where we discussed scenario 1, please go back and do that. In that video, we talked about how when we are at standard temperature and pressure, 1 mole of gas will always have a volume of 22.4 liters. And so we can use that 1 mole is 22.4 liters as a molar conversion in that case. If we are not at standard temperature and pressure, then we need to use the ideal gas law, which is what we're going to discuss in scenario 2. So if our reaction is not taking place at STP, so we don't have standard temperature and standard pressure, then we need to take into account what the temperature or that pressure is, and we cannot use that 22.4 liters for 1 mole of gas. Note that this scenario you can use in any case. You can use what we're going to talk about at STP, and you will get the correct answer, but you have to use this if you are not dealing with standard temperature or pressure conditions. And so in this process, we will end up needing to do 2 calculations or 2 parts. We're going to need to use some stoichiometry, and then we are going to need to use the ideal gas law, which is PV equals nRT. And we can do stoichiometry when we have moles of gas, and then N is equal to moles of gas. And so that's our connecting point, is the moles of our gas. Looking at number 4, I have the reaction for us. It is the same reaction that we saw in that first set of notes. So hydrogen gas and lithium hydroxide are produced when lithium metal is added to water. If you have 32.7 grams of water, so we have 32.7 grams, what temperature is needed to produce 16.1 liters of hydrogen gas with a pressure of 98.2 kilopascals? Anytime we are given temperature information, temperature and pressure information, it applies to everything in our reaction, but it only impacts the gas. And so I'm going to just list those under the gas. I know that I'm looking for what temperature is needed to produce. Well, the gas is going to be able to change volume, 16.1 liters, with a pressure of 98.2 kPa. Well, in order to get to that temperature, we are going to need to do stoichiometry to find something. And that something we need to find is moles. Remember that N, the variable, is moles. Our first step is that we are going to do stoichiometry because we have 32.7 grams of H2O, and we can then find how many moles of hydrogen gas we have. So that is a 2-step stoichiometry problem that we've done in the past. Once we've found that, then in our second step, we can use that ideal gas law in order to find what that temperature is. All right, so 32.7 grams of H2O. We know that 1 mole of any substance is equal to the molar mass in grams. We can use our periodic table to find that. So I need to get from grams to moles in order to use my mole ratio. So grams of H2O, or 1 mole of H2O, we can go to our periodic table and add up 2 hydrogens and 1 oxygen. We get 18.015. Then I need to get rid of my moles of H2O, and I want moles of hydrogen because that is what I need to find the moles of. Using our coefficients from our balanced chemical reaction, we have just 1 mole of hydrogen to 2 moles of H2O, and so we're going to plug those in. And now we can go ahead and do that calculation. So when I plug that into my calculator, I get 0.90757, and that is moles of H2O, moles of hydrogen, and that is our N value. I'm going to leave more digits than my sig figs just because we're not done with our problem yet. If we are to kind of round this here, that means our next answer is not going to be as accurate. And so now in part 2, I'm going to use that ideal gas law with the moles that I now know. I now know this value is 0.90757 moles. And I then have enough of my variables to use that ideal gas law and to solve for an unknown. All right, so now as we look, let's do the second part of that problem, because again, we ultimately want to find that temperature. Well, we know for a gas, pressure times volume equals moles times R times T. We are now going to have pressure. I am given volume, we just found moles, and I'm looking for temperature, I'm looking for T, and we don't want to forget that we know R because that is our gas constant. And so we know that R is that 8.314 from our formula sheet. So now we can go through, we can solve for temperature, however you prefer to solve. If you want to go through and plug these in, we've got 98.2 times volume, 16.1, that's in our standard units. We know our moles from up above. I'm going to just leave that in my calculator. And then R is 8.314 times T is what we're looking for. And then however it makes most sense for you to do this calculation, if you prefer to go through and multiply these out and then divide by whatever this is to get T by itself, you can. I usually will just leave these exact, and then when I go ahead and find my temperature, I'm going to be taking that 98.2 times 16.1 divided by that 0.90757 times that 8.314. We do have to make sure we're dividing by both of these, so make sure you give that a try in your calculator. And I get out 209.53. Now let's go back and look at our sig figs from kind of our original given numbers. We have 3 sig figs in our volume. I've got 3 sig figs in my pressure. R has 4 sig figs, and then we had 3 sig figs in that amount of H2O. So let's keep 3 sig figs. We're going to keep our hundreds, 10. Let's round to the nearest whole number. And so we're going to have 210, and that unit for temperature is Kelvin. We also need our little decimal there to make that those 3 sig figs. So with these, we're always going to be doing 2 steps. We're going to do a stoichiometry with moles, either starting or ending, and then we're using those moles in that ideal gas law. We could end up needing to do the ideal gas law first to find moles, and then doing stoichiometry at the end. But both, anytime we're doing this, it'll be kind of those 2 steps. So let's look at number 5. Hydrogen gas and oxygen gas combine to form water vapor. How many liters of water can be made from 55 grams of oxygen gas and an excess of hydrogen at a pressure of 362 kPa and a temperature of 85 degrees Celsius? So an excess of hydrogen just means we don't have to worry about hydrogen in our problem. We have enough. I'm going to go ahead and look at what I have. So we've got 55 grams of oxygen gas. And again, I like to kind of list them below the chemical. And then we're looking for how many liters of water. And so we're looking for the volume of water can be made. And then we have pressure and temperature. That applies to everything in our problem, but because we're looking at volume of H2O, Volume is the only thing it's going to impact. It's not going to impact the mass of our gas, and this one we don't have to worry about hydrogen. So I'm going to list those down below. We've got the pressure is 362 kPa, and a temperature of 85 degrees Celsius. I'm going to convert that to Kelvin, so add 273, and that's going to be 358 Kelvin is the temperature. And whatever we're dealing with kind of those gas relationships with, we are going to at some point need moles in order to use that ideal gas law. So thinking of what do I have, what do I need? Well, if I'm doing anything with my gas, I have two unknowns. This I already have, and so just like in our last problem, we are going to first do that stoichiometry. We're going to go 55 grams of O2 to find how many moles of H2O. And then after we know moles of H2O, we'll be able to use that ideal gas law with those values. So we've got 55 grams of O2. I'm getting rid of grams. I want moles, and 1 mole is molar mass. So we've got that, nope, I need to multiply that by 2 because it's diatomic, 31.998. And then using our mole ratio, moles of oxygen, we want moles of H2O. And so we're going to have 2 moles of H2O to 1 mole of oxygen. And I can go ahead and do that calculation to figure out, well, how many moles of H2O will be produced? And I get 3.437, and that's going to continue moles of H2O. And I'm going to kind of keep that in my calculator, or at least keep past my sig figs, so I'm not cutting off too many digits. And now this we know is Rn. So we have now that moles value. We found what that is. That 3.437 moles. We don't necessarily need to write that there. And now we have pressure, temperature, and moles. We have enough that we can use ideal gas law to find our volume. So to do that, we're going to take that PV equals nRT. Let's plug in what we know. We know the pressure. We know we're looking for the volume. We know N is 3.437. I'm going to just keep that in my calculator or keep more digits than sig figs. R, that 8.314 times T, 358. And again, we have all of our standard units that match the units on our gas constant. And this one, when I'm solving to get V by itself, I'm going to just need to divide both sides by 362. If it makes more sense in your head, go ahead and write out the step where you multiply all these together before you do that division. But that division will cancel on the left, meaning that we're going to get a volume of 28.26, and that continues. And now that we're ready to find our final answer, we can do sig figs. And I always just go back to, what did I start with? My 55 grams is 2 sig figs. I've got 3 sig figs. I've got 2 sig figs from here. And when we're adding that, since we're looking at digits after the decimal, it ends up going up. So 2 sig figs there. Other things that have sig figs are molar masses, and usually a molar mass has 4 or 5 sig figs, and so that's not going to determine our sig figs. So let's keep 2 sig figs. So we're going to keep the tens place and the ones place. So we're going to have 25, and our standard unit is liters for volume. So 28 liters is my final answer. All right, if you want to go ahead and try number 6 on your own, go ahead and do that. I went and listed out everything I have, and then I'll kind of talk through how this is different. Feel free to pause. So with this one, we are asked for how many grams of nitrogen are needed. So we're looking for grams of nitrogen. We're given volume of ammonia gas, we're given pressure and temperature, even though all of these will be affected by pressure and temperature, because we're talking about ammonia gas, I just listed those under there. So we have volume, pressure, temperature. Anytime we're dealing with whatever specific gas it's asking about, that's what we need to know moles of. So looking at what I have now, in order to find these grams, I'm going to need to know moles first. So my first step is going to be to find those moles using my ideal gas law. So using that pressure, volume, temperature, we can find moles, PV equals nRT. Once we have found, and that is moles of that NH3, then we can go and do our Stoich. So in this one, our steps are just flipped from what they were in those first two. Now that I've found moles, I can go moles of NH3 to moles of nitrogen, and then 2 grams. So that's our second step, is the moles to grams, and there is my work. So we take the moles from our ideal gas law. Again, let's not round this until the very end. And so we'll have those moles of NH3. We're going to use our mole ratio to get to moles of nitrogen, and then to get to grams of nitrogen. When we're done, this is the value that I have in my calculator. I think I have my decimal off. So this is supposed to be, I think, 21.2278. And then with that, we've got, sorry, 21.2278. And then let's look at our sig figs. So we've got 3 sig figs, 3 sig figs, 3 sig figs, and the molar mass we had 5 sig figs. So we're going to keep our tens place, our ones place, and we'll round to the nearest 10. Reach out to your teacher with any questions. That is the end of our scenario 2 solution, gas stoichiometry for when a reaction is taking place at conditions that are not standard temperature and pressure.